Okay, section 9.4 is about odds and expected values. There's actually two completely separate topics within this section that we're going to take a look at. The first one being odds. So if we have an event, we're going to call P of A the probability of the event happening, and P of A bar the probability it doesn't happen, because A bar is a complement of A, right? Everything not in A. So the probability is that the event doesn't occur, sorry. The odds of the event A are the probability of event A divided by the probability of event A complement, or the probability of event A divided by 1 minus the probability of event A, or often we'll count based on what the argument's looking at, and we'll actually count the number of items in event A and the number of items not in event A. Sorry, guys. Let me do an example, and I think it will make it very clear. Okay? What we're going to be doing basically is we're going to be counting the number of ways something can happen versus the number of ways it won't happen. And the next example will show you that. The odds against an event is just the flip of a fraction. It's reciprocal. So I can take all these fractions I did on the first part and I can flip it upside down. I think we'll see what happens. So, are we okay with switching the screen? Okay, we've got a container of marbles. Okay, you're reaching in, kind of like our box problems where you're reaching in, drawing letters with blocks, we're drawing marbles in a box. We have 5 red and 3 white marbles, total of 8 marbles. Okay, so if we're wanting to know the probability that we will choose a red, this is old stuff. We've done this before. What's the probability that I reach in and I choose a red marble? 5 eighths, right? I reach in, I draw a red out of the total 8. So the issue is that what I do is I take the number that I want, the number of, let's say, desired outcome. Right? If the desired outcome is a red, that's the number of ways I can get the desired outcome. And I divide it by the number of total possible choices. That's what I do for probabilities, right? We've been doing that. Okay, odds does this. Odds says I reach in and I draw out the red. How many reds are there? 5. Instead of dividing by the number of ways that I could have gotten anything, I divide it by the number of ways that are not red, which is 3 in this one. So if I'm describing it the way that I just did, this is the number of desired outcome, the number of ways I can get what I want, and I divide it by the number of ways to, oh, so that's good. Right. Number of ways I don't get my desired outcome. Okay, so when you hear, and I've never been to a horse race, but when you hear about horse races you hear about people talk about the odds of winning a race. The odds are 2 to 1. Well, that means 2 times out of every 3 times they'll win. Because 2 to 1 means 2 times they win, 1 time they lose. Okay, this one, 5 times you win, winning is a red marble, 3 times you lose. Okay, it's a ratio of winning to losing instead of a ratio of winning to the whole thing. All right, so let's do it with a percent now. All right, so if the probability of rain is 60%, the probability written as a percent, what are the odds against it raining? Okay, so the probability, oops. As a fraction is what? Okay, 60 out of 100, you can write it as 0.6. I'm going to write it as a fraction though. So we'll do 60 out of 100. Right? Percent means out of 100. 60 out of 100. Which means that if I want to do the odds, that it will, well, and let's say the probability, this is the probability it will rain. This is the probability then that it won't. What's the probability it won't rain? 40 out of 100. So if I want the odds, this says odds against. I can't spell anything today. The odds against it raining, okay? What am I going to do? I'm going to put it won't on top, and I'm going to put what it will do on bottom. Okay, the odds that it won't do what I'm wanting, which is about the raining, is it won't rain. And the bottom, what goes in the bottom is the probability that it will rain. So you can do this in one of two ways. We had three definitions for how to do probability and odds connected, right? Three definitions back here on slide 2. Three different things written down. So let me do it with one of them, and you'll see that we could have done it maybe with another, and it's probably half of you are going to think one way and half the other anyway. If I want to do the odds against, I can take the probability that it won't rain, which is 40 out of 100, and then divide by the probability it will rain, which is 60 out of 100. But we've worked with fractions. Fortunately, that's right. So what are we going to do? What could we do with this? Multiply. Okay, so we can multiply by the reciprocal, right? And what happens to my 100s? So this gives me 40 over 60. Do you think I'm going to leave it that way? No. But it will reduce pretty quickly to 2/3. So the odds are 2 to 3 that it'll rain. In other words, if I had 5 different things that could happen, twice it's going to not rain, rather than the odds against it rain, and 3 times it's going to rain. So we have the not on top, and we've got happening on bottom. Odds against it raining. The odds against it raining are 2 to 3. Okay, I'm going to show you one other way to think about the problem. The other thing you could do is you could do the odds against. You know, the odds against is supposed to be the probability that's not going to happen over the probability that it will. And you could leave your values written in as percents. You wouldn't have to change them into two fractions. So what's the probability that will not rain? 40%, and the probability it will rain? 60. And the percents do what? They what? They reduce, they cancel, right? I mean, if you divide a percent by a percent, they go away. Okay. And the zeros do as well, and then I can reduce the 4 and the 6 just like I could before. This will still be 2/3. And there is no more percents because they reduce, they cancel one another. Think about it directly from a percent perspective if you like. Questions on this? Okay, so I've been using some language as I've said things that might have not made clear sense to you. And what I was using was based on this next description. This talks about the odds of an event and the odds against an event. I should say event. So if I have the odds of an event, and another way of writing odds is writing it as just a ratio like this. We've seen this ratio notation before, right, with the colon between them. 2 to 3, or whatever. Then we can find the probability of the event by taking the number of ways that the event happens and dividing by the two different numbers, that is the number of ways it happens and the number of ways it doesn't happen, to get back to a probability. So a minute ago, oops, I'm sorry, I used the 2/3 as an example. I said, if I was given 5, where'd my 5 come from? No, I want to use this, just this number I was going to use here. I'm using a 2 over 3, and I said, if I had 5 ways, where did I get 5? I added. Okay, that's my one point, was that I added the 2 and the 3. That's where my 5 came from in that discussion a moment ago. I added, because 2 is the number of ways it doesn't rain, 3 is the number of ways it does. Which means the total number of options in the reduced form anyway was 5. 2 plus 3, 5. Okay? That's what's going on in this denominator. This is the number of ways something happens plus the number of ways it doesn't. And the number on top then is the number of ways that something happens. Down here, same thing, except you see that instead of the top being an M, it's an N, which is representing the number of ways something does not happen. Okay, so this is the number of ways N that it does happen. N is the number of ways it doesn't happen. If you want to turn things back into a probability, you simply add the number of ways something happens and the number of ways something doesn't happen together for your denominator. Let's do one so you can see what happens. We've got a 3-child family, because they're fun to work with, right? And it says, what are the odds, excuse me, of having all of the same gender? So one way to do this is a tree diagram. I'm going to show you another way to think about the problem. So we've done, some of you have done contemporary math with me when we did organized list. So if we have the first child, it could be a girl. And if we have a second child, it could also be a girl. And we could have a girl as a third child. That's one option, right? Now, I'm not going to be totally random in what I'm doing. I'm going to change things one at a time. So I could go girl, girl, girl. I could have 2 girls first and then have a boy. That's my family. Or maybe I don't, and this is the only way I can have 2 girls at the front, right? 2 girls and a girl, 2 girls and 1 more boy. I could have a girl first and had a boy second. And then I could have had a girl. Or I could have had a girl first and a boy second and had a boy. And there are other options for having a girl first. I've listed every option out. And if you don't like this, it's fine. You can draw a tree diagram and it'll work just as well. But I also could have started out with a boy. And what could I have had? 2 more boys. That'll work. So I could have had boy, boy, boy. Or I could have had boy, boy, girl. Or I could have had boy, girl, boy, or boy, girl, girl. And these are all my options. They're all equally likely. You can remember that from your tree diagram. All the branches have 1/2 all the way along them. So they all end up being a 1/8 probability when I'm done. We're all good on that. All right, so this one says the odds of having the same gender of children. So how many of these have the same gender? 2. Those 2, right? So how do I get odds? Well, the way I get odds is I get the number of ways of win, and win is defined as whatever the description was I'm trying to satisfy. Okay, so in this case, the winning is having all the same gender of children. Okay. Over the number of ways I lose. And lose just means I don't get the desired outcome, whatever that description satisfies. So how many ways do I win here? 2. And how many ways do I lose? 6. And this reduces to 1/3. This is a 1 to 3 odds. There's one way that it would happen out of every 3 times it doesn't. If I were to collect 1,000,000 families, all with 3 children, 1 out of every 4 families, or for every 1 family that had the children all matching children, 3 families wouldn't. Okay? All right, now the odds against having the same gender of children. That's 3 to 1. Do you have to show any work? No, not really, because what do? You just flip the fraction. don't reduce this. This does not equal 3 then, otherwise it's not a ratio, it doesn't make any sense. If it bothers you to leave it written that way, you can write it as a ratio like this. Sometimes that helps people to think about it that way. It means the same thing. But if it bothers you to have left something written with a 3 over 1, change it to 3:1. Okay, that's odds. You're going to work some odds problems. The other thing in this category, in this section, is expected value. If we have a possible outcomes of an experiment, there we have the ends of the branches of the tree diagram, okay, all the different branches. And we give them a name. This one's A1, and this one's A2, and this is A3, all the way down to however many outcomes we have. And each of those branches has a probability. This is just the picture we've been working with. And the way that we get expected value is we take, call it E, we take the event A1 times its probability plus the event A2 times its probability all the way down to event AN times its probability. In order to make any sense of that, we've got to talk about numbers for everything, right? So I can't talk about an experiment that is involving having children now. But I could talk about an event or an experiment that's involving rolling a die. Because they come up, they don't come up with a letter or anything, right? They come up with 1 through 6. So I can work with that. As long as I'm working with numbers, I can talk about expected value. Expected value comes in most handy, perhaps, when I'm talking about money. We're going to do a money example before we're done. A fair game is a game whose expected value is 0. Okay? So when people talk about going to like Las Vegas and they'll say something like, it's better to play this game versus that game. We make those kind of claims. So it's better to play blackjack versus the slots or something like that. They're talking about this issue of fairness. How likely am I to win? The more likely I am to win, the more reasonable it is to play that game versus some other game. That's what they're talking about. They're talking about this idea of fairness. And this doesn't mean fair like my children say fair. That is, you got what I wanted. Okay, that's not what we're talking about. We're talking about from a very mathematical perspective on this. Okay, so I'm going to show you an example. I was talking with my mother this week, and I was telling her that I really enjoy teaching about probabilities because I get to show you all of the interesting things about my family. Maybe not all of them, but there are interesting things that happen. So this example is my tribute to my father-in-law, who is a wonderful man. He's a smart man. This is something he does that I just sigh when he does it. Okay? On a roulette wheel, there are numbers 0, 0, 0, and 1 through 36. So how many numbers are there on a roulette wheel? There's 38. There's 38 different slots. So imagine a giant spinner split up into 38 slots. If you've never seen a roulette wheel, it looks just like a spinner, with twister and stuff like that. And you just spin it with 38 little slots. Okay? All right. If a ball lands on your number, you receive 35 chips plus the chip you originally played. Okay, everybody with me? All right. First question, what is the probability that the ball will land on 0, 0? That is 1 out of 38. Right? There's 38 slots. If they're all equal, and they are, then it's going to be a 1 out of 38 chance of that happening. This is very close to what happens when my father-in-law passes the roulette wheel. By the way, he's not a compulsive gambler or anything like that. It's not like that. But this is something he does. When he passes a roulette wheel, if he sees, okay, so let me tell you one more backstory about a roulette wheel. There is a board next to a roulette wheel that tells you the past however many, I'm not sure how far it goes back, but however many spins it's landed on. It'll tell you that it's landed on 2, and then 7, and then 12, and then 56 is an example. About 36, and then it landed on 0, and then it landed on 12 again, and then it landed on 5, and it shows the recent history, if you will, of the spins. Okay? So in essence, it would do the same thing if you stood there for a while and were just paying attention. Okay? All right, so when my father-in-law passes a roulette wheel, if he sees that it has not landed on 0, 0 in recent history, he will bet on 0, 0. My math mind says, all right. If he bets one chip, and that one chip is worth $10, what is the expected value of his bet? This is the question. So let me show you again how expected value works. Expected value, E, is the probability, well, let's say it this way, the value of the win, let's say it that way, the value of the win times the probability that you win, plus the value that you lose, or value that you lose, times the probability you lose. That's how you do expected value. And there may be more than one win. I mean, you may be able to win, you know, $5 if this event happens, and then $3 if this event happens, and nothing if this third event happens. So it may not be a two-case scenario. Right? This one is, you either win and you get a bunch of money, or you lose and you lose your first chip. Okay, everybody with me? All right. So it says, back up here at the beginning, it says that if you win, you get 35 chips plus the chip you played. So how many chips do you get if you win? 36. But one of them was your money to start with, right? So you didn't really win 36 chips. You really won 35 chips. Get your one back, but you really won 35. And how much is the chip worth? $10. So how much do you win if you win this particular game? 350. And what's the probability that you will win? 1 out of 38, because we did that on part A. What is the value if you lose? -10, right? Because they keep your chip, and your chip was worth $10. Okay, everybody with me? You are down $10 in your wallet if you do not win this game. And that right there is the reason why I can't stand to go to the casino, because I'm scared to death of losing my hard-earned money, because I earned it. I don't want to play a game that I might not get it back at. Okay, so what's the probability that you lose? 37 out of 38, right? 37 out of 38 times, you will not get your money back. All right, so we're going to run some numbers, and you can do these numbers in your calculator with some decimals. Remember, at the end, this is money. So whatever you're doing in your calculator needs to have at least 2 decimals of accuracy, and then at the end, be rounded to 2 decimals of accuracy. So I'm going to let Marissa tell me some numbers. Marissa, let's do the first one. What's 35 times 1 over 38? With 3 decimals. Oh, I'm sorry, yes, 350 times 1 over 38. 9.21. Is there a number after the 1?
A 0.
210?
Yeah.
Okay, so 211. All right. And I'm going to subtract because the next number is going to be a negative. What is 10 times 37 over 38? 737?
Yes.
Okay. And then let's subtract 9.211 minus 9.737. Which would be negative 53, right? 0.53, because this is money. So negative 53 cents. So if I go and I play the game, quote unquote, infinitely many times, on average, I will lose about 50 cents every time I play. Okay? Make sense? So is this a good deal? Is the game fair? How do you know the game's not fair? Should have got a 0 at the end if the game were fair. If the game were fair, it would have been, in a grand number of schemes of times of playing this game, it would be equally likely for me to win and lose. And it's not, right? The expected value is actually negative, which means it's more likely that I lose, which is why the casinos are so nice. Make no mistake, they're beautiful for a reason, right? Some of them around Oklahoma, I don't know if they are. They don't look that nice from the outside. All right. Have you seen the show Deal or No Deal?
Yes.
Okay. And in fact, they have Deal or No Deal inside of arcades. Have you seen those? Chuck E. Cheese has one. My daughter likes to play that one. In the television show Deal or No Deal, a contestant is down to 2 cases with equal probabilities of being chosen. The cases have $250,000 and $1. If the game is fair, and by fair I don't mean the expected value of 0 business here, I just mean it's equally likely. Okay, if it's actually a fair game, nobody rigged it, in other words, right? Nobody's playing dirty. And you are the banker, what would you offer the contestant as a deal? So we're going to do the same kind of idea. In this case, your expected value can't be 0 because you're going to win something. Okay, at the very minimum, you win $1. Heaven forbid, that would be sad. But that's a possibility, right? All right, so what is the probability that you win? Or the probability times the outcome each time. And we only have 2 outcomes here, just like on the last one. So we're taking probabilities times outcomes. So what is the first probability? 1/2. Both probabilities are 1/2, right? What's the first outcome? Give me one outcome. What could happen? You could be the big winner and get $250,000. What's the other probability? 1/2, right? With an outcome of $1. All right, so you're going to take your calculator, or you should be able to do some of this in your head. Do all of it, to be honest, in your head. What is $250,000 times 1/2? Yeah, it's $125,000. And what is 1/2 times 1? 0.5. And then what's $125,000 plus 0.5? 50 cents. So if you're the banker, you should be offering about $125,000, give or take, right? To the contestant to walk away. I would walk away. That would be nice pocket change. It would be very nice. All right, this is one of my favorite examples because I think it relates a little bit to some of the things that you guys will see when you start getting into the politics of education. So let's take a look. In the cartoon at the beginning of the section, the odds against winning the lottery were 55 million to 1. Okay, so here's the back, you can see that. What is the probability then of winning the lottery? So we haven't done a probability versus odds problem yet. But if the probability, if the odds against are 55 million to 1, what is the probability that it will happen? 1 out of 55 million and 1. 55 million 1. Okay? Because what it means, remember, for odds is it means the number of ways something happens compared to the number of ways it doesn't. And then with the odds against, which is what this one is, odds against, the number of ways that you lose, 55 million ways you lose, or times that you would lose out of the one time you would win. Are you with me? So out of every 55 million one time you play, one time you will win. That's what that says. All right. The grand prize is $13,567. Sorry, is that wrong? $13,567,290, and the ticket costs $1. Is the game fair? So how do we decide if the game is fair? We do expected value. Expected value has to do with winning and the likelihood that will happen, time plus losing and the likelihood that will happen. So if you win, how much do you win? Very enticing, right? I know if I tried to give you $13 million, you would take it as long as there were no strings attached. You would. And how likely is that to happen? How likely is that to happen? 1 out of 55 million and 1. But that's only one side of the coin. You also could lose. In fact, we didn't quite give the right answer just a minute ago. What's wrong with what I wrote? You had to pay $1 to play the game. So if you only bought one ticket, it's actually $2.89. Okay, did everybody catch why it's $2.89? Because now's the time to ask if you didn't. Okay, what happens if you lose? You lose $1. So your winnings are -1, and this is such a common thing that if you lose too much, you can claim it on your taxes. I'm not kidding. Yeah. Oh yeah. All right, so how likely are you going to lose? math all the time, right? Yeah. Okay, 55 million divided by 55 million, 1. Almost. Well, for all intents and purposes, all the time. All right, so grab your calculator. Find out for me what happens. Okay, some of your calculators will let you enter this all the way. If they won't, write down some digits as you go like we did in the last problem. I just want to know what your answer is at the end. What do you get? Negative 75 cents. $75. Remember, please don't make your notation on that. So on average, with the game set up in this way, every time you play the lottery, you should expect to lose on average 75 cents. We're actually going to get into our next problem. Very good question. So let's take a look at what this means really. And this is where it comes into effect for you. As with many state lotteries, the proceeds are often said to benefit education. Have you ever heard that before? Yes. One of the reasons why Ohio, when we were up there, actually ended up passing a law to allow casinos is because the money was said to benefit education. The state lottery here in Oklahoma years ago, and within what I remember at least, same thing. They were saying it was going to benefit education. So let's take a look at what that would mean. Under these conditions, if all proceeds benefit education and 1 million tickets are sold, okay, we're going to have to tell you how many tickets are sold to make sense of the problem. What is the expected value generated for education from the lottery? All right, so Haley asked, does that mean on the last problem that for every ticket sold, on average, right, that the lottery benefits 75 cents? And the answer is yes. So if you're out of 75 cents in your pocket, it's in somebody else's pocket in this case. In this case, it would be the description as it's described, education, right? So somebody tell me what the number was before you rounded it to 75 cents. Can you give me some more numbers?
75.
What was it? 3-3. We'll go with 4 decimals. That's probably sufficient. So for every ticket that has been purchased, 75.33 cents of it, right, is not given back to whoever purchased it. It's been kept by whoever is running the lottery. And how many tickets are there? 1 million. Okay. So if I take this number times 1 million, and I really don't need the negative. I'm about to make a claim here in a minute that this is actually from the perspective of the lottery, how much money is generated as opposed to how much money is lost by the consumer. But if I take this times 1 million, what number do I get? $753,300. So this is benefit to the lottery. That is the money that the lottery raised. Think fundraiser here, although that's not a good description, okay? This is the amount of money that was raised by having done this, okay? Now, what are the actual probabilities that could be going towards education? That's the question. What's really happening here? Because really, that's not what's happening. That's what happens on average, right? Are you guys with me? That's on average things. But what really happens when we run this system one time, okay? Well, one possibility is that no one wins. Agreed? There's no winner. And if there is no winner, then we sold 1 million tickets for how much? $1 a piece. So how much money was really raised? $1 million, right? If no one wins, we take the tickets, the number of tickets, times the ticket price. In this case, it was 1 million tickets times $1 per ticket for $1 million. So one possibility is that $1 million is raised. That is one legitimate possibility. And you guys do realize that with the lottery, the way it is, no one has to win. People use this description term that, well, somebody's got to win. No, they don't. That's why those numbers keep going up on the signs that you see on the highway. It's because nobody won. Nobody won. More money went back into the system, so they raised the number on the sign in hopes that people will go out and buy more tickets. Nobody has to win. Did somebody eventually end up winning? Yeah. But nobody has to win when they pull that number out of the hat. None of those numbers have to match. All right? Item number 2, or possibility number 2, is that somebody wins. And usually when somebody wins, there's several people that win, and they actually end up splitting it. They don't each get $1 million. That's not the way it works, whatever the number was, okay? So they each actually split the pot. So the way all the lotteries work is split the pot when they win. Has anybody ever seen anything happen to you? Where's my brain movies now? Nobody sees them. It's so sad. It makes me feel so old. Meg Ryan and Nicolas Cage. It's a cute movie. And it's about lottery, and it's a cute one, okay? Promise it is. All right, so here's the deal with you got a winner, right? So if you have a winner, you still brought in $1 million of income, right? But what happens? You had to give the winner their winnings. So you still raised $1 million. That is, people still paid $1 million to play the game. The problem is that you had to pay out some money. How much was your payout? Last slide, what did it say? Nope.
13.
Yes, say it loud for us, Green.
13,567,290.
The payout's $13 million. What happened to the fundraiser for education? It owes money now. Does this sound like a good plan to you? So if we do this, what do we get? Negative what? 12,567,290. So we owe money from the lottery. Oh yeah, that sounds good. Let's increase the taxes. That'll help the situation, won't it? Sure will. All right, so this is what happens a lot of times with a lot of these different things. So you cannot be both in support of the lottery because it raises money for education and not realizing the fact that in order to be supporting the money because it's raising money for education, you are also supporting the fact that people are losing their money, right? Like almost all the time, because if they didn't lose their money almost all the time, the money would be raised for education, right? And this is how these bills are always passed, is they're always passed on this sort of, idea that they're going to raise money for this purpose. And one of two things either happens. You raise money for the purpose, and the individual people who were silly enough to contribute the money in that way are out their money. Or somebody wins the money, in which case we didn't raise money for the purpose we were doing it for. You can't have it both ways. Okay? Now, are the numbers this drastically off? No, right? You're trying to get the numbers closer together so that we're not in a deficit or a surplus of so many. So you might see that this number, we have sold 1 million tickets, maybe they sold 13 million tickets, right? So they sold 13 million tickets, our number wouldn't be quite so off. Agreed? And then we would be looking at it from that perspective. All right.